Hey, this is Mr. Ayton. This is week 30 for Unit 13 Thermochemistry, and this is pre-AP Chemistry. What have we taken a look at in thermo so far? We've taken a look at exothermic, endothermic. We've taken a look at calorimetry and an experimental way to find the enthalpy. We've taken a look at the enthalpies of formation, product mass reactants. We've looked at bond enthalpies. And last but not least, we're going to look at Hess's law to calculate the enthalpy. We'll also look at entropy and Gibbs free energy. So let's first start with Hess's law of heat summation. This is another way to calculate your enthalpy or your delta H. And this is when we've been given a list of reactions, So if you have a list of reactions, if you have enthalpies of formation, you know you're going to do products minus reactants. If you have bond enthalpies, you're going to draw the bonds. But here for Hess's law of heat summation, we have been given a list of reactions. So you can see we can do two things to a reaction. We can either flip that reaction, which changes the sign of the delta H from positive to negative, or if you double or triple or so on and so forth, it doubles the delta H as well. And then you're going to add all the chemical reactions together, which is why they call it Hess's law of heat summation, okay? So here, take a look. We have a reaction that we want to know the delta H. We don't know the delta H, but we want to know it. We have hydrogen gas and half a mole of oxygen gas making gaseous water. And we have a list of reactions, which they gave me the enthalpies for. So what you're going to do is you're going to find the thing that's unique in the reaction. So you can see how I have H2 gas right here, and I want H2 gas right here. Okay, H2 gas is on the reactants. It's already in the reactants. I don't have to do anything to this. I have 1 mole of H2 gas, 1 mole of H2 gas, so I'm going to keep this the same. I don't have to flip them. I don't have to multiply or divide. Now let's take a look at the second reaction. The second reaction, we see, look at what's in the second reaction that's in the reaction that I want. Do you see H2O gas right here? And we have H2O gas right here. You can see we have 1 mole and 1 mole. We don't have to double it or anything. But we have the H2O gas as a product, and here it's a reactant. So I have to flip this, don't I? I have to flip this delta H. And that changes that delta H to positive 44 kilojoules per mole. And you can see we kept the first one the same, negative 286 kilojoules per mole. Can you guess what we're going to do with these two delta H's? We're just going to add them up. So negative 286 plus 44 ends up giving me a delta H for my reaction of this reaction up here is negative 242 kilojoules per mole. Negative 242 kilojoules per mole, which means it's an exothermic reaction. And I hope you can see when we flip this second reaction, the liquid water is on the reactant side, which cancels out with the liquid water in the products here when we add everything up. And we're left with the half a mole of O2, which is in my final reaction. But what you want to really do is zero in on the things that are unique to the reaction, okay? Let's take a look at one more example here. You can see we want to know this delta H for this reaction at the end here, okay, this reaction at the end. So what we're going to do is we have a list of reactions. We have actually 3 reactions here. We're going to go through each reaction and see, can I find something that's going to be in my final reaction? Well, let's take a look at the first reaction here. What's in this first reaction that's in my final reaction is this 2NH3 gas, Can you see how that's a product here? And I want it to be a reactant. So what am I going to have to do? I'm going to have to flip this reaction, which makes this positive 92 kilojoules per mole. Let's take a look at the second reaction. Is there anything in the second reaction that's in my final reaction? Well, you might go, well, H2. Well, do you see how H2 is in more than one reaction? So don't look at the H2. You're going to look at the things that are unique to the reaction. So let's take a look at the liquid water. We have 2 moles of liquid water, but we want 4 moles of liquid water on the other side. So we're going to have to flip this reaction, and we're going to have to multiply it by 2. So we're going to have to flip the H2O on this side, and we're going to have to double it to become 4. So that makes negative 572 become positive 572, and we have to double it. So that gives me positive 1144 kilojoules per mole. Now let's look at the third and final reaction. Can you see how we have NO2, and there's two NO2s, which means we don't have to multiply or divide or anything. It's on the products, so I'm going to keep it the same. So it's positive 66. We kept this guy the same, didn't we? Now you might say, Ayton, what about this H2 gas? Well, remember the H2 gas will work itself out. Remember we flipped this H2 right here on the other side, so that was 3 of them. And do you remember in the second reaction, we flipped this and doubled it, so that became 4 H2s on the other side, which added up to the 7 H2s. It all worked itself out. So just look at the things that are very unique, and everything else will work itself out. And what are we going to do to find the delta H of this reaction? We're going to add all of this up. And so I'm at 1144, 92, 66, and that gives me positive 1302 kilojoules per mole. That's an endothermic reaction. And you can see we use Hess's law of heat summation to calculate the delta H. Okay? There's a term that I need you to know, and it's called entropy. Entropy is the degree of disorder or randomness in a system. It's about the dispersion of particles. And remember how delta H was negative for exo, delta H is positive for endo? Well, delta S is positive for a greater dispersion of particles. So you can see how we're going from definitely, this is a solid, to definitely a gas here, which means our delta S, not delta H, our delta S is going to be positive because we have a greater dispersion of particles. But take a look at the second example. The second example is we're going from a gas to a solid. That's less dispersion of particles, which means your delta S would be negative for this example. And so you can see things like aqueous, things like gases are going to have very high dispersion of particles, which means those delta S's are usually going to be positive. Things like solids and liquids, normally going to have negative delta S's. Also, if you have more moles of gas, more moles of a substance, obviously more moles means more particles. There's a greater dispersion of particles. That would be a positive delta S as well. So delta S is called entropy because entropy begins with the letter S, of course. Okay? And last but not least, here's some examples. Let's go to a few more examples here. Is we have a solid becoming a solid and a gas. Can you see how we have 1 mole of solid going to 2 moles, and it's going to a gas, which means my delta S is going to be positive. There's a greater dispersion of particles, especially since we're making a gaseous substance. And here, take a look at the second example. We have 2 NH3 gases making nitrogen gas and 3 hydrogen gases. We haven't changed the states of matter, but what have we changed? We've changed from 2 particles to 4 total moles of particles, which means we have a greater dispersion of particles as well. Your delta S would be positive, Okay, we're going to finish up with Gibbs free energy. Gibbs free energy is delta G, and Gibbs free energy tells how favorable a reaction will be. Will a reaction occur favorably? Well, keep in mind, that's given if there's enough activation energy. If there's enough energy to break all the bonds, okay, will the reaction be favorable? And you can see a negative sign for that, for delta G. A negative sign means it is favorable to occur. And so I want to just take a look at one quick example of this. And this would be propane gas, C3H8 gas. And we're going to combust this bad boy. We're going to burn this gas, okay? Now keep in mind this propane gas is in a sealed container, isn't it? Which means as it comes out and we start to burn it, can you see how we're making a whole bunch of gaseous water, we're making a whole bunch of carbon dioxide gas, we're making a whole bunch of particles, which means your delta S is going to be positive. We go from a pressurized container of propane to these water molecules and these gaseous carbon dioxide molecules. They are free. And so that is the delta S is going to be positive. Well, guess what? Does this absorb heat or release heat? a combustion reaction is ultimately going to release heat, won't it? It's going to be exothermic. It's going to make all the surroundings go up in temperature. So we can take a look at this equation. Delta G equals delta H minus T delta S. And our delta H is negative. It's a negative value. And you can see our delta S is minus temperature. Delta S, my delta S is a positive value because I was going towards more disorder, a greater dispersion of particles. Now let me ask you, if you take a negative number minus a positive number, will you ever get a positive value? No way. A negative value minus a positive is always going to give you a negative, which means for a combustion reaction, this delta G is negative, which means this reaction will be favorable. If you have a little spark, this reaction is going to occur in all temperatures. So every temperature, this reaction will occur. And we call that Gibbs free energy. Well, that finishes out Unit 13, homies. This is Thermochemistry, Week 30, Pre-AP Chemistry. I'm Mr. Ayton, and I'm awesome, yo. So I'll catch you in class. Bye-bye.